Why delta of reduced voltage starters? In this presentation, we're going to be looking at the process as well as how this system functions. And we're also going to investigate at the end some unique equipment sizing considerations. Why delta motor starters can be used with only 6 or 12 lead three-phase motors. And that's because we need to have access to both ends of the windings inside the motor. The motor windings are started in Y and then transition to run in delta configuration. Now, due to this, there's no reduction in line voltage to the motor at start. However, the voltage across the windings changes from Y to a delta configuration. This is an example of a 6-lead motor where you can see we have a definite access to both ends of all 3 of the windings. This is going to show us a Y delta open transition motor starter. Closed transition do exist. However, this is the most common application to learn how the system functions. In this Y delta open transition reduced voltage starter, we have a timer relay in much the same fashion as the previous reduced voltage starters, where they are going to change state after a set period of time has elapsed. There is also an S and a 2M control relay, which are connected through a mechanical interlock, allowing only one to articulate or move and close its contacts at any given moment. Well, let's energize the system and press the start push button. At which point, whoa, a lot of things energize immediately. So we have the timer relay, which energizes. We have 1M that energizes, and also S, which energizes. Now, these are going to now change the state of all of the contacts that they are connected to. There are power contacts as well as some control contacts. We have all of the power contacts changing state to closed. We have a holding contact going to closed, and we have a electrical interlock in series with 2M that goes to an open state. At this point, the motor is going to be energized in Y. And this means that it's going to have a voltage across each one of those individual windings, √3 smaller than what the line voltage is. In this case, because we have a 208 volt three-phase line system, there's 120 volts across each one of the motor windings. Now, this is a significant reduction of voltage. Now, the timer relay will continue to count down, and once it's completed, the timer relay contacts that are timer related will change state. One of them closes, the other opens. In doing this, we see that the S coil is de-energized, and the S coil controls a control contact as well as 2 power contacts. At this point, the power contact breaks the connection of that star configuration, and in the control circuit, we see that we have an established electrical connection now through the 2M coil. Now, the ramifications of this step is that although the motor windings are theoretically energized, there's no current flowing through them. And because of that, there's 0 volts being measured across them. Now, if there's 0 volts and 0 current, it means we have 0 torque, and that's why this is considered an open transition motor starter. So our 2M coil is now going to energize, and when it does, it will close or open, depending on the contacts, from its energized state. So the 2M close, and in the power circuit and the control circuit, the 2M electrical interlock will open. And when this happens, we now have a connection back to the line conductors. Now we have 208 volts across each of the motor windings, and this motor is now in a run condition. Notice the overload heater location in the power circuit. They're all in series with each motor winding, meaning they will only ever carry the phase current. This is very unique and the only type of starter that we look at which has this particular orientation. This means that if we had a motor FLA of 20 amps, we would anticipate that the line current coming into the line side of the motor starter was 20 amps. Then it would split And it wouldn't split in half, it would split in reference to a root 3 correlation. So 11.5 amps is what we would measure. And you can imagine this as the tip of the connection point between two phases of a delta connected load. At this point, we have phase current and phase current, and you can see the phase current is going to be flowing through the overload heaters. Now remember, an overload heater is there to protect the motor from an overload condition. So it must be sized appropriately for the value of current that would be expected under normal operating conditions. And so to size the overload heaters for a Y delta starter, an electrician must first calculate the motor's phase current, and then after that is done, can apply whatever multiplier is necessary as per the Section 28 requirements. Y delta closed transition motor starters do exist, and they are a little bit more complicated. They introduce a bank of resistors that allows for the motor to remain energized throughout the process of start to run. We're not going to go through this one in the same depth of detail that we did with the open transition. Here's an example of a Y delta starter. You'll notice that it's fairly simple. We have a timer relay, we have three contactors and an overcurrent. There are no heat generating load devices such as resistors or even transformers. And so for that sake, it is considered to be one of the more common mechanical reduced voltage starters because it is so simple and it's so cheap.